This is the GTX 990 Ti graphics card released in June 2015. Its average computing power is 2.5 million calculations. After 6 years, the RTX 3080 was released with over 3.5 times the performance of the GTX 980 and a 40% increase in computing power. Not long after, the RTX 4090 was introduced. Not only have graphics cards become more powerful, but CPUs have also grown stronger. Previously, the i7-7700K CPU consumed around 120 watts and was considered a small heater. Today, it's not uncommon for the i9-13900K CPU to consume up to 280 watts. When choosing a power supply, if you select one that's too small, the machine may shut down unexpectedly or restart under high loads. Conversely, if you choose one that's too large, you'll not only waste money, but also feel the pinch. With increasing power demands, selecting the right power supply capacity is crucial. If you're considering choosing a power supply, you first need to understand its function. Household outlets provide 220-volt alternating current AC, but computers require low-voltage direct current DC. The main function of a power supply is to convert AC to DC and provide various voltage levels. After the 220-volt 50 Hz current enters the power supply through the outlet, it passes through an EMI filter, PFC, rectifier filter, and transformer. The voltage is then reduced to 12 volts, 5 volts, and 3.3 volts and sent to the computer components via cables. In a computer, the CPU and graphics card are the two components that consume the most power. They primarily use the main power supply to operate, but the operating voltage of the CPU is only about 1.3 volts. Therefore, when power is supplied to the motherboard, it must pass through MOSFETs around the CPU to reduce the voltage to the necessary 1.3 volts. Similarly, the operating voltage of the graphics card core is also only about 1.1 volts. When current enters the graphics card through the PC power supply, it also needs to be stepped down before being supplied to the graphics card core. The power rating of a power supply is measured as rated power, which is the maximum power that the supply can continuously provide under stable conditions. For example, a 1 kilowatt power supply can deliver a total of 996 watts through its official outputs. Two main outputs of this power supply can deliver up to 83 amps, equivalent to 996 watts. The 5-volt and 3.3-volt outputs can provide separate currents up to 250,000 lines, and the total simultaneous output power of these outputs does not exceed 125 watts. The -12-volt output is now hardly needed for computers, and its power is quite low, so it can be ignored. When the computer enters standby mode, the power supply mainly provides low power. Meanwhile, the actual output power of the power supply will be adjusted flexibly according to the computer's needs. If the computer only requires 500 watts, the power supply will only provide 500 watts, not necessarily reaching 1 kilowatts at all times. Therefore, choosing a power supply with too high a rating can lead to waste and does not improve system performance. To understand better, you may have heard about conversion efficiency. Simply put, during the conversion from AC to DC, the power supply generates some losses and dissipates heat. This means that the rated power of the power supply does not include these losses. For example, if a power supply is rated at 500 watts with a conversion efficiency of 90%, the DC output will be 500 watts. However, to achieve a 500 watt output, the input needs about 555 watts, 500 watts divided by 90%. Approximately 55 watts will be lost as heat. Therefore, most power supplies are equipped with fans for cooling and heat dissipation. The efficiency rating of a power supply will vary with the load and follows a curve like this. Typically, the efficiency is highest when the load is between 40% and 60%. The better the quality of the power supply, the higher the efficiency curve will be. Certifications like gold and silver correspond to higher efficiency, while bronze ratings are also sufficient in many cases. For example, this 1 kilowatt power supply is platinum rated. However, when choosing a power supply, it is not necessary to select one with twice the computer's power requirements. The best performance is achieved with a power supply that matches the load, which both saves energy and optimizes costs. Investing too much in a power supply may not provide proportional value. In general, for a home computer, The two largest power consumers are the CPU and the graphics card. Therefore, when selecting a power supply, you should consider the consumption of these two components. If you have some knowledge about computer hardware, you are likely familiar with the concept of TDP, thermal design power. TDP is a set of data provided by the manufacturer related to the power consumption of a hardware component. However, whether it's a CPU or a graphics card, relying on TDP to estimate actual power usage is not reliable. For example, the TDP of the Intel 13900K CPU is listed as 125 watts, but in reality, when the cooling solution allows and the CPU runs at maximum frequency, it can consume up to 280 watts. This discrepancy is mainly because different manufacturers have their own definitions of TDP, and different brands apply different standards. Additionally, advancements in technologies like Turbo Boost or Precision Boost Overdrive, PBO, also allow for optimization and maximization of the chip's potential, leading to higher power consumption than the published TDP. Furthermore, some devices experience significant fluctuations in peak power. As a result, TDP is no longer a reliable reference value for consumers. For CPUs, the standard we commonly use to evaluate performance is the FPU single-threaded test. This is a feature of system stability testing software that allows the CPU to perform complex calculations with 64 processing cores. During the test, the CPU runs through highly complex tasks, creating a high load. Through the IW4 sensor, you can monitor the CPU's average power consumption in real time. For graphics cards, a similar metric is GDP, which represents the maximum power consumption when the card is operating at full capacity. Software like Furmark is typically used for testing, forcing the graphics card to render complex objects and create a very high load. Combined with GPU-Z software, you can read data from the graphics card's sensors. When the PWR status is displayed, it means the graphics card has reached its maximum power consumption. However, whether it's a CPU or a graphics card, they do not operate with a fixed power consumption level. Instead, billions of tiny transistors continuously toggle on and off, causing power consumption to be unstable and fluctuate in pulses. If you use a highly accurate measuring device, such as an oscilloscope, and a sufficiently precise current probe to check the power consumption of a graphics card while gaming, you will see a continuously fluctuating graph. Even though the average consumption might be 285 watts, it actually fluctuates quite significantly. In software like GPU-Z or Afterburner, this value is also shown as 285 watts. Even when using multiple power measurement devices, the outlets may show that the entire system consumes only around 300 watts. However, the actual power consumption of the graphics card can reach up to 380 watts. The CPU operates in a similar manner. Inside a CPU, there are many components such as the arithmetic logic unit, ALU, memory buses, and controllers. In stress tests like the FPU stress test, usually only components like the ALU and cache experience high load. However, when the CPU is in actual operation, all components can be activated simultaneously. This means that in a very short period, the CPU can reach power consumption levels far exceeding what occurs during tests, leading to higher than expected power figures. That's why, during overclocking, even if many people have meticulously adjusted parameters and encounter no issues during stress tests, they might still experience blue screens when running a series of games. So when choosing a power supply, do we need to monitor the maximum consumption of both the graphics card and CPU to ensure sufficient headroom? The answer is not necessarily. Most quality power supplies can handle a small overload for a short period without issue, until the overload protection feature activates and the power supply shuts down. For example, the ROG Thor 1000 watt has an overload protection point OPP of 1,434 watts, while the GX 850 has an OPP of 1,285 watts. Typically, the higher the quality of the power supply, the longer the allowable overload time and the higher the overload capacity. However, not everyone has specialized equipment like probes or peak measurement tools to check each hardware component in detail. Accurately assessing the maximum power consumption of the entire system is also not an easy task. Therefore, I recommend using software tools like FPU stress tests and Furmark to calculate the maximum average consumption of the entire system. This is the simplest and most intuitive method for most people to assess the appropriate power supply. However, when selecting a power supply, you need to leave a certain margin to handle peak loads and minimize the risk of performance drops. But how do you know how many watts the CPU and graphics card you plan to buy will consume before you officially purchase the components? It's quite simple. You just need to be proficient in using search tools. You can look up reviews for the CPU or graphics card you want to buy on platforms like Google, Baidu, or technology forums. Most professional media conduct detailed power consumption tests using tools like FPU or Furmark. You can also refer to power consumption values provided by other users on forums. However, it's important to note that due to the complex chip architecture, manufacturing processes can create slight variations between CPUs. This means that voltage stability and power consumption can vary a bit between components. These differences can also be influenced by the motherboard's tuning. It is completely normal for power consumption to fluctuate by several watts between different reviews. For example, with the CPU 13700K, around 220 watts are sufficient to achieve maximum performance. However, some CPUs might consume up to 260 watts due to uneven silicon quality or higher voltage supplied by the motherboard, which is also a normal phenomenon. Once you determine the power consumption of the CPU and graphics card, calculating the power for other components becomes easier. First is the memory. For instance, with DDR5 7200 MHz, C34 16GB x 2 memory, during stress testing, each RGB-enabled memory stick consumes about 4.3 watts at full load. Without RGB lighting, the power consumption decreases. DDR4 memory consumes a bit more, but even with RGB lights, it typically does not exceed 6 to 7 watts. Therefore, we can estimate the total power for 2 memory sticks at around 12 watts. Next is the storage. For SSDs like the Samsung 990 Pro, one of the high-end solid-state drives, the maximum power consumption is around 6.5 watts, and it usually fluctuates around 5 watts. We can average this to 6 watts for an SSD. For mechanical hard drives, during startup, due to the need to spin up the disk to 7,200 RPM, it consumes more power during the startup phase and then drops to a steady-state consumption. According to testing by my colleague Arfar A2, with the HC550 18 terabyte hard drive, startup power consumption can reach 18 watts, while idle consumption is about 5 watts, and full load is around 9 watts. During startup, the CPU and graphics card typically do not operate at maximum power, so the power supply will have sufficient overhead to handle the hard drives. Moreover, power supplies also have short-term overload tolerance. Therefore, we can disregard the startup current and estimate an average power consumption of 10 watts for each hard drive. Additionally, the motherboard contains components such as the sound card, network card, USB interfaces, and other devices, all of which consume power. The power consumption of these components is quite difficult to measure accurately, as it depends on many factors such as the number of USB ports, connected devices, and the presence of fast-charging USB interfaces. Hence, we estimate around 30 watts for these components. And here is the case fan. On the back of the motor, you can see the rated voltage and current, which is typically 12 volts and 0.2 amps. Multiplying these two values gives us a power output of 2.4 watts. However, it's important to note that this figure represents the fan running at full speed. In practice, most computer fans don't run at full power. Nowadays, many fans also come with RGB lighting, so for safety and calculations, we will assume each fan consumes around 4 watts. When installing 3 fans at the front and 2 or 3 at the rear, you could need up to 7 fans in total. This requires a power consumption of approximately 28 watts. The next step is to sum up all the power consumption. Basically, this gives you the average power consumption of the entire system when running at full load. According to this example configuration, the total power consumption could reach nearly 656 watts. But keep in mind, this 656 watt figure refers to the power usage when all hardware is operating at full capacity. In most real-world cases, the computer typically only utilizes 2 or 3 major components, so the actual power consumption will be lower. It's unlikely that the CPU, GPU, hard drive, fans, and memory will all operate at maximum load simultaneously. When the system runs at high load during everyday tasks, it's highly probable that it will only consume around 450 to 550 watts. So, is a 650 watt power supply enough? The answer is no. Running at high load for extended periods will increase the internal temperature of the power supply, which can negatively affect its lifespan. Moreover, when the power supply operates at high load, the fan will spin faster, generating more noise. Some power supplies, due to their design and internal structure, may experience reduced efficiency under high load conditions, which can negatively impact the user experience. Additionally, there's the issue of power spikes we mentioned earlier. Although many power supplies have a certain level of overload capacity, the quality of each brand, materials, and design varies. There are very few detailed reviews that test the overload capacity of power supplies online. So, it's difficult to know exactly how much overload a power supply can handle and for how long. Therefore, when choosing a power supply, you should leave some power headroom. This not only prevents the power supply from running at high load continuously, but also helps the system handle unexpected power spikes. To sum up, with a configuration that includes the 13900K and 4070 Titan, my personal recommendation is to use a 750 watt or 850 watt power supply. Finally, I'll leave you with a question to solidify this information. This is the hardware of a configuration from a computer store. Take a moment to calculate this setup and see which power supply is the most appropriate. In my opinion, a 550 watt power supply is suitable. Not sure if everyone agrees with me. With the 5600X CPU, based on online searches, you can see that when running in PBO mode, it can consume around 130 watts. The 3060 graphics card, based on what you can find online, consumes around 170 watts. 2 RAM sticks consume 12 watts, the SSD consumes 6 watts, the motherboard and USB devices consume about 30 watts. Adding in 5 cooling fans and case fans, which consume around 20 watts. So the total power consumption of the entire system, when all components are running at full load, is around 370 watts. To handle power spikes and leave some headroom, a 450 watt power supply could meet the demand. However, as many manufacturers have gradually stopped producing 450 watt models, there will be fewer high-quality options in the future. And the price difference between 450 watt and 550 watt power supplies is usually only about 30 to 40 units. Therefore, I recommend going for a 550 watt power supply to ensure stability. Similar to when you search for information online, find the power figures that others have tested and add them to your own results. Always leave a certain margin of extra capacity so you can determine the necessary power supply. Every time I live stream, many people ask, how many watts does this CPU and that graphics card require? Instead of just providing a specific number, why don't we learn how to calculate it? Teaching others how to calculate is more beneficial than simply giving them the answer. That's the purpose of this program. I hope that after watching, you will no longer be confused when choosing a power supply.